Okay, let's set up a coordinate plane so that we can refer to our loop in different dimensions. I'm going to set up the y and the x, and I'm also going to put a z-axis on my plane where the positive z is going to be out of the page because magnetic quantities always involve three directions. I'm then going to place a magnetic field, quantity B, in blue, going in the positive x direction. Okay, I will add to my picture my loop. So I'm going to make a loop around on the xy plane, centering it on the y-axis. I'm going to call the longest dimension L and the widest dimension W for length and width. I'm going to pivot my loop so that it's free to spin on the y-axis. And I can add more than one loop of current, which I'm doing now, so my answers will be reflected by N. My current is going to go around counterclockwise, right, which you can sweep with your fingers. When you do that, your thumb will show you the direction of the B that the loop will make. We're not specifically interested in that right now. What we're going to do is evaluate the force on each section. So looking at the right section, you can set up your right hand with the eye pointed up. Your B will point to the right, and that will indicate that on the right section, there's an inward force on that wire. Repeat this for the other side. Tilt your fingers to point down, B to the right, the rest of your fingers, and your thumb points out. The bottom, you realize, has no cross product, and same with the top. They'll each experience a zero force due to the right hand rule. Once you see this, you realize that the loop is being pulled out on the left into the right. It's going to rotate. See the directions in purple there? What makes it rotate? A torque from the force. The magnetic force creates a torque. To write out that torque, the force is created at a distance r away from the pivot. So torque is r cross F. F here can be filled in using ILB. Notice there are actually two forces, so when we sum them up, let's multiply by 2. Let's also rewrite R, because we can relate it to W. R is just half the width, W over 2. That'll cancel our 2's. We'll have IBLW. LW, length times width, that's area. So let's replace those terms LW with the idea of area. Okay, next let's address there's actually more than one loop. So we'll multiply our entire torque expression by N. Once we've done this, we have redefined a quantity called mu. We invent this quantity, magnetic moment, in order to discuss loops whose area might be a different shape. The magnetic moment is NIA, number of loops, current, and area. To find the direction of a magnetic moment, because it is a vector quantity, wrap your fingers in the direction of I. Your thumb will point in the direction of the magnetic moment. Trying here, you see that your thumb points outward. The magnetic moment is directed outward for this loop. Always perpendicular, just like an area vector should be. So as time goes on, this loop's going to begin to rotate, gaining speed as it turns, and it'll find itself in the YZ plane sometime later, looking like this, with its magnetic moment aligned to the B. But it's been gaining speed, going too fast. It can't stop here, right? So it's going to continue rotating around until it's completely reversed from the way it was before and looks like this. But at that moment, it's maximum torquing the other way, rotating back around, finding itself in that location in the ZY plane with the mu and the B aligned. Again, just going too fast. So now the loop rotates back to its beginning condition with maximum torque, restoring it to rotate the other way. So as you can imagine, as friction takes over, right, the system's velocity will be damped, and the magnetic moment will eventually align with B. This is the equilibrium position, the stable equilibrium, in which if you evaluate the torques, you won't be able to find any on the loop. So in equilibrium, mu and B align. You'll realize that anywhere you evaluate the force, it's just canceled out by the force on the opposite side of the loop. No cross product, stable equilibrium, no net torque, no net force. Now, you might be wondering about a B and a mu that are perfectly misaligned. That's going to create an unstable equilibrium for us. Yes, the forces will all cancel out and the cross product will give us 0, but any slight oscillation of the loop will then cause it to spin around, because the mu is showing the direction of the magnetic field the loop creates. So then we know that magnetic fields want to align north to north, right? And that you can get them to align in the opposite way, but it's extremely unstable.